every single nuance of how a computer is built and operates. This is why, when you hear this sound, that is a warning that I am making massive oversimplifications, which I'm sure you'll point out to me in the comments. That was the warning for the entire video. Modern computers at their core are electrical circuits. A very simple circuit might consist of a battery connected to a switch, then a light bulb, then back to the negative terminal of the battery. Modern computer components typically supply a voltage of 3.3 or 5 volts between the positive terminal and the ground, or negative terminal if you like to think of it that way. Computers treat information as binary, on or off, true or false, 1 or 0, based on if the voltage is high or low. The important component in our circuit here is the push switch, which comes in two flavors. Push to make, that's when a person presses down and the circuit is completed between the two terminals and the bulb lights up. The push to break switch is exactly the opposite. This is the symbol for a transistor. More specifically, it's a metal oxide semiconductor field effect transistor, or MOSFET. Its source and drain are like the two terminals of a switch, but it has a third terminal called a gate. Just like switches, there are two types. The N-channel type makes a circuit when a high voltage is applied to the gate, like a push to make. The P-channel breaks the circuit when a high voltage is applied, like a push to break. So transistors act like switches, except instead of a person pressing it down, a voltage is applied. So channel circuit are like that, and the switch comes in two or on to the computers. That was the warning for the entire video. Modern computers at their core are electrical circuits. A very simple circuit might consist of a battery connected to a switch, then a light bulb, then back to the negative terminal of the battery. Modern computer components typically supply a voltage of 3.3 or 5 volts between the positive terminal and the ground, or negative terminal if you like to think of it that way. Computers treat information as binary, on or off, true or false, 1 or 0, based on if the voltage is high or low. The important component in our circuit here is the push switch, which comes in two flavors. Push to make, that's when a person presses down and the circuit is completed between the two terminals and the bulb lights up. The push to break switch is exactly the opposite. This is the symbol for a transistor. More specifically, it's a metal oxide semiconductor field effect transistor, or MOSFET. Its source and drain are like the two terminals of a switch, but it has a third terminal called a gate. Just like switches, there are two types. The N-channel type makes a circuit when a high voltage is applied to the gate, like a push to make. The P-channel breaks the circuit when a high voltage is applied, like a push to break. So transistors act like switches, except instead of a person pressing it down, a voltage is applied. In modern computers, these types of transistors are used in pairs, referred to as CMOS, or complementary metal oxide semiconductor. The gate terminals of a given pair are always connected together, so they receive the same input. Here is a simple example. If we apply a high voltage, or 1, to the input, the N-channel MOSFET opens a route between high voltage and the output. The P-channel closes the route to ground. If we apply low voltage, or 0, at the input, the P-channel opens a path to ground. Okay, so this circuit seems pointless. We got the same thing at the output as we did at the input. But let's swap around the two MOSFETs. Now, when we apply a high voltage input, a low output get referred to the gain drain is set down on if the voltage is high or low. The important component in our circuit here is the push switch, which comes in two flavors. Push to make, that's when a person presses down and the circuit is completed between the two terminals and the bulb lights up. The push to break switch is exactly the opposite. This is the symbol for a transistor. More specifically, it's a metal oxide semiconductor field effect transistor, or MOSFET. Its source and drain are like the two terminals of a switch, but it has a third terminal called a gate. Just like switches, there are two types. The N-channel type makes a circuit when a high voltage is applied to the gate, like a push to make. The P-channel breaks the circuit when a high voltage is applied, like a push to brake. So transistors act like switches, except instead of a person pressing it down, a voltage is applied. In modern computers, these types of transistors are used in pairs, referred to as CMOS, or complementary metal oxide semiconductor. The gate terminals of a given pair are always connected together, so they receive the same input. Here is a simple example. If we apply a high voltage, or 1, to the input, the N-channel MOSFET opens a route between high voltage and the output. The P-channel closes the route to ground. If we apply a low voltage or 0 at the input, the P-channel opens a path to ground. Okay, so this circuit seems pointless. We got the same thing at the output as we did at the input. But let's swap around the two MOSFETs. Now, when we apply high voltage, or 1, to the input, the N-type opens a route to low voltage, or 0. When we apply a 0 to the input, we get a 1 at the output. Whatever we put in at the input, we get the opposite at the output. Later, we will come back to how this forms the basis of all modern processors. Understand that it is vast networks of CMOS pairs like these which allow computers to think. For now, let's see how transistor networks are made in basic terms. Silicon is a semiconductor with 4 valence electrons, which is doped or mixed with other elements. Gallium, for example, has 3 valence electrons, 1 less than silicon, hence more positive, or p-type. Meanwhile, an element like arsenic has 5 valence electrons, 1 more than silicon, therefore adding a negative charge, hence n-type. Trace amounts of these elements, typically 1 for every million silicon atoms or so, are implanted by chemical diffusion or by firing them out of a particle accelerator. Transistors are made by sandwiching a region of one of the dopants between 2 of the other. Let's look more closely at the N-channel configuration. This by itself does not conduct electricity, but when an electric field is applied to it, a conducting channel forms, hence the name field effect transistor. This can be thought of in simple terms as the electric field attracting electrons from the N-doped region, which has a surplus, to the P-doped region, which has a deficit. Near the semiconductor stack, we have a conducting electrical terminal. When it's at high voltage, an electric field forms and the transistor conducts. But, to stop a short circuit, we need to add an insulating layer between them. The contact is metal, the insulator is silicon oxide, and finally we have the doped semiconductor, hence the term MOSFET. For a computer, we need millions of interconnected CMOS pairs, and they must be small and close together so that electrical signals can travel between them quickly. Making a processor typically begins with a solid block of p-doped silicon called a die. Transistors are then created on top of the die by a process called lithography, writing on stone. There are 2 main techniques used in lithography. The first is deposition, chemically building up a layer of controlled, predetermined thickness across the entire die. This means that, for example, N-doped silicon can be coated all over the top of the p-doped die. Unwanted surface material is then removed by a second technique called etching. This is done by applying chemicals or hot plasma to the top of the die. Several steps are taken to ensure that the etching is targeted at specific areas, and therefore material is removed selectively. A chemical termed a photoresist is deposited onto the die. Light is shined through a mask, exposing predetermined areas of the photoresist. The exposed areas must be the same size or larger than the wavelength of light used. Hence, very short wavelength ultraviolet light is used for lithography. A special etching method is used to remove only regions of photoresist which were exposed and nothing else. This opens up gaps in the photoresist, and then another etching method is used which targets everything except the unexposed photoresist. Finally, the remaining photoresist is etched away. As a result, material has been removed wherever there are any gaps in the mask. The 2 techniques of deposition and etching used in conjunction mean that the N-type dopants for all the transistors on the die can be added simultaneously. Next, the silicon oxide is deposited and etched, and finally metal is deposited and etched away to leave metal channels on top of the die. These metal features form not just the conducting terminals of the transistors, but also the tracks, equivalent to wires in a circuit, which connect the transistors as required. Every time photoresist is deposited, exposed through a mask, gaps are made and a die is etched. Finally, the billions of transistors are assembled and connected together by this method. There may be 3 CMOS pairs with 3 different inputs, then going out to 4 different CMOS pairs somewhere else, and so on and so on. To summarize, computers handle information as ones and zeros, when voltage in an electrical circuit is either high or low. Transistors act as electronic switches, changing between these two states. The transistors always come in complementary pairs, so when one half of the pair opens, the other closes. Lithography is the process by which huge numbers of interconnected transistors are built up on a block of silicon. To understand why transistor networks are useful, we need to talk about a branch of mathematical logic called Boolean algebra. Rather than go into the full gory mathematical details, I will just illustrate the basic concepts with some not too serious examples. Let's say some friends are choosing a restaurant. Alice is happy when the restaurant serves burgers. Bob is happy when the restaurant does not serve burgers. We can think of evaluating restaurants in this case as something called a gate, an object which takes a binary input, true or false, 1 or 0, and returns a binary output. In this case, the input is whether the restaurant has burgers, and the output is if someone is happy with the restaurant. For Alice, the gate is simple. The output is the same as the input. In electronic terms, the circuit is just a connection. For Bob, the gate is what's unimaginatively called a NOT gate. This is the symbol typically used to denote it. In the previous section, we have seen how this CMOS pair acts as a NOT gate. Let's consider a more interesting example when the logic gates can have multiple inputs. Such gates have pretty straightforward names, as we'll see. Now the friends are choosing restaurants which might serve pizza, noodles, both, or neither. Alice is happy when the restaurant serves at least one of the two options, or both. This idea is represented by what is called an OR gate. This is the symbol. Bob wants choice, so he wants both pizza and noodles on the menu, hence the AND gate. Charlie likes it if the restaurant serves pizza or noodles, but not both. Let's say she thinks that they wouldn't do a good job if they weren't specialized enough. The corresponding gate is called exclusive OR, XOR for short. Each of these gates also has a complementary gate, basically the same gate with a NOT gate after it. For example, the NAND gate gives a 0 when all its inputs are 1, and gives a 1 otherwise. These complementary gates are denoted by the usual symbol with a circle at the output. For a computer, these and all other possible gates must be implemented through CMOS pairs. Connecting two pairs as follows creates a NAND gate. The N-channel and P-channel transistors still work in pairs. Only when a high voltage, or 1, is applied to both pairs of inputs do the paths to high voltage close and the path to ground opens, so a 0 is output. This is exactly the behavior of a NAND gate. The NAND gate is important because it's what's called universal. This means that any other gate can be created out of NAND gates, as long as there are enough of them. Now, there are more efficient ways to make certain gates, but in essence this means that the problem of implementing logic gates through CMOS pairs is solved. There are also gates with 3, 4, or as many inputs as necessary. For example, take two AND gates connected as shown here, and they simply become a 3-input AND gate, and so on and so forth. To summarize, logic gates are conceptual mathematical objects which allow us to make deductions based on binary true or false statements. For example, if it's true that today is Saturday or today is Sunday, then it's also true that today is the weekend. We have now seen how the CMOS pairs from the last section can be used to practically implement these gates in terms of electronic binary logic. Now we shall see how computers handle numbers and use logic gate networks to do arithmetic. We are all used to base 10 numbers, meaning that there are 10 digits from 0 to 9. The digits represent multiples of powers of 10, which are 1, 10, 100, 1000, and so on. Modern computers use base 2 numbers, with just 2 digits, 0 and 1. Binary digits are multiples of powers of 2, which are 1, 2, 4, 8, and so on. For example, in base 10, the number 953 is 9 times 100 plus 5 times 10 plus 3 times 1. In binary, the number 101 is 1 times 4 plus 0 times 2 plus 1 times 1, which is 5 in base 10. Any number in base 10 can be represented by a number in base 2 and vice versa. To represent the number 101, 3 electrical tracks in order would have their voltage on, off, on. Each of these tracks carries a binary digit or bit. With 3 electrical tracks, this is called a 3-bit number. There are similarly 4-bit numbers, 8-bit numbers, and so on. Of course, the 4-bit number 0101 is equivalent to the 3-bit number 101. Let's consider adding together a pair of 1-bit numbers A and B to get C. 0 plus 0 is 0. 0 plus 1 is 1. What happens when we try to add 1 plus 1 in binary? The same thing as happens when we add 5 plus 5 in regular base 10. There is no digit big enough, so we put a 0 in that column and carry the 1 to the next column. So to guarantee being able to store the result for any possible values of A and B, the result C must be a 2-bit number. The bit on the right is 1 when A or B is 1, but not both. This is the behavior of the XOR gate, if you recall Charlie from the last section. The bit on the left is 1 only if A and B are 1, ergo the AND gate. Therefore C is obtained by connecting A and B to gates like this. When adding numbers A and B larger than 1 bit, things get more complicated with 3 input gates because there is now a bit from A, a bit from B, and a carried bit. As I said in the previous section, NAND gates are universal, meaning that any required gate network can be implemented using enough of them. In base 10, multiplying by 10 is easy. Just add a 0 onto the end of your number. In base 2, the same is true for multiplying by 1 0 in binary or 2 in base 10. So multiplying by the numbers 1 0, 1 0 0, 1 0 0 0 in binary just involves shifting each bit to the left and putting a 0 on the end, which is unimaginatively called a bit shift. What about multiplying by an arbitrary number, say for example 1 1 in binary? This is the same as multiplying by 1 0, multiplying by 1, and adding the two together. So binary multiplication of A by an arbitrary number B works as follows. Begin with 0. If the rightmost bit of B is 1, add A. Bit shift A once, and if the next bit of B is 1, add this to the total. Continue for every bit of B. Computers also rely on making comparisons of numbers, such as, is A equal to B, is A greater than B, and so on. The computer might have the current time in seconds stored as a binary number A, updated every second, and the time to set off an alarm stored as B. The alarm would be made to go off when A is equal to B. To do this, the computer must check that every bit of the number A is the same as the corresponding bit of B. So the XOR gate returns 1 when an input is 1 and the other input is 0. In other words, when its inputs are different. The XNOR gate, which is the complement to the XOR, meaning it returns the opposite to the XOR, therefore returns a 1 when its inputs are the same. A bunch of XNOR gates applied to each pair of bits of A and B return whether those bits are equal or not. The AND gate returns a 1 when all its inputs are 1. So applying it to the XNOR gates returns a single bit, which is 1 if and only if A is equal to B. There are also ways to implement subtraction, division, and other comparisons, all using gate networks. For example, bit shifting the other way divides a number by 2. These are all implemented using transistors etched on a chip. Just a note, when I say the word number in this video, I am referring to an integer, or whole number. There is also a way to store fractions in a binary version of scientific notation, called floating point numbers, or floats. I won't go into how they work, but the general principle outlined here still applies. To summarize, a sequence of binary on-off electrical signals is used by computers to represent a number in base 2, as opposed to base 10, which is used by people day to day. Networks of logic gates can be used to add, subtract, and compare binary numbers, and with a few extra steps, multiply and divide them too. We have seen how circuits composed of transistors can be used to implement addition and other algebra for any number with arbitrary binary digits or bits. If you want to build a computer, we would have to choose exactly how many electrical tracks and gates to have available for representing a number. This is like when you're filling in a form and it has a set number of boxes physically printed on it for putting in your age. For commercial computers, this is always a multiple of 8. 8 bits are called a byte. The computer will have adder circuits and so on of the types I described in the last section, which take 1 byte or 8-bit numbers, 2 byte or 16-bit numbers, 4 byte or 32-bit numbers as inputs. No matter of how many bytes a number is comprised, one of its bits can be set aside to denote a plus or minus sign. When a number is signed in this way, if the leading bit is 0, then the number is positive. If the leading bit is 1, then the number is negative. As anyone who has ever taken a mathematics exam knows, it's important to store your workings. Whichever operation a computer undertakes, the inputs and outputs must be somehow stored. To do this, a type of circuit called a latch is used. Once it has latched, it will stay that way for a long time and can therefore be used to store a bit of data. 8 latches store a byte and so on. This is an example of what's called a D-latch, comprised of NAND gates. You may notice that this looks rather strange. Before, we have seen gates in a strictly sequential manner, where the output of one gate goes directly to another. Now, there is an output from one going to the input of another, but then the output comes right back. It is this kind of interconnection that allows this network of gates to hold and retain its output value, 0 or 1. Nothing will change unless the E or enable input is 1. When enable is 1, whatever bit is applied to D will propagate to the output. The computer will carry out an operation, addition for example, enable a bunch of latch circuits to store the output, and then switch the enable back off. The result will then be held there as long as is required. 8 of these latches can form a register which will store a byte of data as long as it's required. An add circuit of the type you looked at in the previous section would have such registers to store the inputs before the addition takes place, and a register to capture the result of the addition. It takes some small but significant amount of time for electrical signals to propagate, for transistors to finish switching and so on. To guarantee that the operation is fully carried out before attempting to read out the answer, all computers have a clock. In basic terms, an oscillating crystal switches a voltage on and off at a very specific rate. At the time when this video was made, computer processors have typical clock speeds of 2 GHz, meaning that the clock switches at 2 billion times a second. The regular switching allows events to be synchronized. To fully carry out an addition operation, it would take at least 3 clock cycles. On the first clock cycle, numbers would be loaded into the input registers. Then, the addition circuit can work over the next clock cycle. Finally, on the third clock cycle, the output register gets an enable signal and stores the result. Actually, most operations take much longer than 1 or even 3 clock cycles to carry out. We have seen in the previous section that multiplication takes several adding steps to accomplish. Nonetheless, whether it takes 1 or 100 cycles, the clock is still used to synchronize when an operation begins until the output is ready. All the so-called arithmetic logic, that is, all the arrays of logic gates which do addition and subtraction, is physically located together with the registers on a chip called the processor, or central processing unit. There are also circuits in there called the cache, which nowadays can store tens of kilobytes of data as their intermediate stages of calculations, for example. There is a need for a larger and longer-term way to store many more bytes of data than the registers and the cache. Computers have separate physical chips of random access memory, or RAM, which makes use of capacitors to store this data. If a capacitor is charged, it has a high voltage and therefore a value of 1. If it's discharged, it has 0 volts relative to ground and so is 0. The charge leaks or is lost over time, but is topped up by the memory circuits as long as the computer is powered. A typical laptop computer has tens of gigabytes or billions of bytes of RAM. Every byte stored in RAM has its own address, like a postbox in an apartment block. The address is itself a binary number. The RAM has many transistors forming gate networks which ensure that when it receives the address in binary format from the processor, it then returns the byte stored at that address. Until recently, computers wouldn't usually have more than 4 gigabytes of RAM. Each of those bytes requires a unique address, so memory addresses were 32-bit numbers. Such 32-bit numbers go up to just over 4 billion, so that used to be fine. When RAM got bigger, there effectively weren't enough addresses, so now 64-bit numbers are used for memory addresses. This is the difference between 32 and 64-bit programs. So let's say you're playing a video game where you have a number of coins in your wallet. The video game will keep track of the address where the wallet total is stored. If you found 8 more coins, the game will fetch the number currently in your wallet from that address, load it into the register, load a binary number corresponding to 8 and base 10 into the other register, add them together and put the result back into the address with the wallet total. We will look at this in more detail in the next section. Each of the bytes also has its own separate address. A laptop or personal computer can store hundreds of gigabytes on a hard disk. There are other technologies like flash memory, DVDs and so on that I won't go into here. The fundamental limit on how fast a computer can do operations is the speed of light, which can go about 15 centimeters or half a foot during a typical computer clock cycle. So it would take multiple cycles for a computer larger than that to fetch any data. Realistically, transistors switch much slower than that, while a hard disk takes time to spin up and scan to read the data. In terms of types of computer memory, the cache is small but quick to access. The RAM stores many more bytes of data but takes longer to read. The hard disk takes the longest to read but stores a lot of data almost permanently. So there is a trade-off between how quickly the data can be retrieved and how much can be stored. From now on in this video, I will explain things as if the computer just has a single pool of memory which it can instantly read. In reality, things are more complicated as I've just described. To summarize, computers have a clock which synchronizes the operations being performed and ensures that there is enough time to finish performing one operation before starting another. Computers process binary numbers in groups of 8 bits called a byte. Registers are used to store numbers during computations, and at other times numbers are stored in the cache, in random access memory, and on a hard disk. Each byte in memory has its own unique address, which is itself a binary number. We have a way of implementing binary operations and storing the results, but the computer needs a way to determine which operation to use and when. This is called an instruction. There are instructions such as add 2 numbers and copy this number. Computers use what's known as the von Neumann architecture, which means that the instructions are stored in memory as binary numbers amongst other data. For example, the instruction number 16 in base 10, or this byte in binary, might mean add together 2 8-bit numbers and store the result. Instruction number 17 might mean the same thing but for 16-bit numbers, and so on. When the computer encounters an instruction, it will use a comparison circuit which we looked at in a previous section to switch on the logic circuit for the necessary operation. If the byte is equal to 16, switch on the add circuit. How does the computer know when a byte is an instruction or not? 16 might be the instruction to add, or it might be the number of coins in a video game. Well, everything has to do with the precise order in which the bytes appear in memory. First comes the instruction byte. If the instruction is to add, the computer will need the 2 memory addresses of the things being added and the memory address where the result is to be stored. Remember that memory is like post boxes for a big apartment building with a unique address on each byte. In the case of modern 64-bit systems, addresses are 8 bytes long. Therefore, the entire add instruction has 1 instruction byte and 24 bytes of addresses, 25 in total. On the other hand, if the instruction is to copy a number, it just needs to be followed by the origin and destination addresses, meaning the whole thing takes 17 bytes in total. The trick is that each type of instruction always takes up a set number of bytes, and crucially, the next instruction immediately follows on after the previous one. So when the computer encounters the add instruction, not only does it carry it out, but it knows that the next instruction is precisely 25 bytes long. To start with, the computer interprets byte number 0, the one at the very start of memory, as an instruction, and thereafter goes from instruction to instruction. Conversely, if there has been an error and the next instruction is not where it's supposed to be, tough luck, the computer will probably crash. How does the computer actually carry out an add instruction? The number from the first address is loaded into one input register and the second address into another input register. The add circuit is enabled and it does the addition. Then, after a sufficient number of clock cycles, the result can be written from the output register to the required address in memory. What happens if the instruction is to add two 16-bit numbers together? The computer simply goes to the address of number A, and instead of getting just one byte, it gets that byte and then one immediately after. The same for number B and the result C. A computer program is a collection of instructions and addresses to be done in order. The computer goes from instruction to make the program run. Let's look at a specific example, part of the game, which is just a program after all, where the player has a wallet with coins in. This is what the contents of memory might look like. Byte number 0 is the instruction to add. Then come two addresses, the address of the wallet total and the number of coins the player has just found. The third address is the wallet again. After the addition, the wallet total will be overwritten. No matter what, the computer will now interpret byte number 25 in memory as an instruction. It is another add instruction, the addresses of the wallet and an amount of coins the player has made from selling items, or the inputs. The wallet addresses the output again. The next instruction is 25 bytes further along, at byte 49. The program keeps going on with millions of other instructions required to make the game function. In this case, the wallet total is being used a lot, so it will probably be held long-term in the processor's cache, as well as the RAM. When the player saves the game, it will be written to a save file on the computer's hard disk. To summarize, the computer interprets certain bytes in memory as instructions for which operation to carry out. Computer programs are stored in memory. They are just large sequences of instructions, memory addresses and numbers. The computer goes from instruction to instruction like clockwork, always knowing based on the type of the current instruction how far along the next one is. So far, we've looked at instructions which work in a linear manner. Copy a number, add two together, and so on. The program would always produce the same result, and eventually it would just get to the end of memory and stop. We need a few more instructions to make a computer what's known as Turing complete. Being Turing complete means that it can eventually carry out any possible computation, load a web page, render a video game, and so on. The only difference between two Turing complete computers is how fast they are at doing those computations. The first type of instruction a computer needs is what's called a jump, or sometimes called a goto. Following the instruction byte is a memory address. As the name suggests, instead of going directly to the next instruction in memory, the program jumps to the specified memory address and carries out the instruction there. This means that the program can now do a loop. In our video game example, we have seen how instructions are used to add numbers of coins to a total kept in a wallet. These instructions, and all the others required to update the game world, render the graphics, and so on, are followed by a jump instruction back to the start. This way, the game can keep running indefinitely. The other crucial type of instruction that a computer needs is a branching or conditional instruction. If a given condition is met, for example if two numbers are equal, then jump to a particular address. We have already seen how a comparison can be implemented with logic gates. Adding such logic makes a jump conditional, allowing different sets of instructions to be executed based on calculations performed so far or inputs to the computer such as a keyboard or mouse. With conditional jumps, the computer is Turing complete. Given enough time, it can do any calculation. At this point, it's worth mentioning how a real program might actually be written. If you thought that things were quite confusing so far, you're not wrong. Remembering which instruction does what, which memory addresses have what data stored in them, where jumps go and so on, this is all hard to keep track of. Programmers typically work with what are referred to as high-level programming languages. This means that all the nuts and bolts of instructions and memory addresses are hidden away and instead life is made easier for the programmer. For example, this is a bit of code in the C or C++ language. This code is readable by humans. If A is greater than B, set Q to be A. Otherwise, when B is greater or equal to A, set Q to be B. In other words, the number Q will end up with whichever number is larger out of A or B. This is easy to understand for the programmer and anyone who tries to read it. A program called a compiler will take this code and arrange it into the correct set of instructions, sort out where the variables are stored in memory, where to jump, do we need to use 16-bit or 32-bit numbers, and so on. This is what's referred to as compiling the code. There are many aspects of programming languages which simplify the job of the programmer, but one of the most important is the idea of a function or method. In mathematics, the square root is a function which takes a number and returns another. Certainly, there are implementations of the square root function in computer code, but there are also more arbitrary functions and methods, such as for fetching emails and so on. Say that a program needs to evaluate the square root of different numbers repeatedly. The instructions which comprise the square root function need only be stored in memory once. Whenever the function needs to be used or called, the computer will jump to the function's location in memory, carry out the instructions, and jump back with the result to the place in the program where it left off. Functions and methods can be compiled into libraries so that programmers across time and space can share useful code that they've written. If you've ever seen a DLL file on Windows, that's what that is. Once a function or method has been written efficiently, other programmers can use it without needing to spend much time on it. To summarize, computers have an instruction to jump to a memory address and carry out whatever instruction is there. This allows loops within programs. Some jumps only happen when a condition is met. Any computer that is capable of such jumps can carry out any computation as long as it has enough memory and time to do so. Chances are you're watching this video on some sort of display. There are many technologies, past and present, which have been used for computer monitors, so I will speak in generalities. Light bulbs, like at the start of the video, are too large, but light-emitting diodes, or LEDs, are smaller and more efficient. The higher the voltage across an LED, the brighter it is. A display is capable of electronically changing the voltage across each of its LEDs, and therefore their brightness, according to data from the computer. Since computers handle numbers in bytes, in other words groups of 8 bits, it makes sense to have the brightness go up on a scale from 0 to 255, the largest value a byte can take. The human eye has cells sensitive to red, green and blue light. By using a set of 3 LEDs, red, green and blue, varying the relative brightness of each one, the human eye can be tricked into perceiving the full spectrum of light. A mix of red and green gives yellows and browns, red and blue gives pinks, all 3 colors at full brightness give white, and at partial brightness give grey, and so on. A little spot composed of 3 colors like this, no matter what technology is used, is called a pixel. A display has pixels arranged in rows and columns to form a 2-dimensional grid. For example, this video at maximum resolution is 1920 pixels in width by 1080 pixels in height. The number of bytes it takes to fill a display in memory is 3 times the width times the height. In simplest terms, the computer must update this many bytes in memory 30 or 60 times per second and send the result to the display. So for example, if you full screen this video in its maximum resolution, each frame would take up this many bytes in memory. While displaying graphics and images may seem like a purely artistic undertaking, and in some sense it is, in actual fact for a computer it is nothing more than gate logic and instructions we have seen so far. Each pixel has a horizontal or X coordinate and a vertical or Y coordinate, which corresponds to its position in memory. For example, let's say your display is exactly 1000 pixels wide and you start with the top left pixel. If you move forward 3000 bytes in memory, or the equivalent of 1000 pixels, you'll go off the end of the top row and onto the left pixel of the second row. There are many algorithms or long lists of instructions to draw windows, buttons, text and computer graphics, all by using this kind of arithmetic and manipulating bytes in memory. To display a simple desktop environment, a loop fills every pixel with the background color by repeatedly copying the sequence of 3 bytes that uniquely defines the color. The taskbar is drawn by looping over only rows of pixels with specific Y coordinates. A start button is created by filling a rectangle with a given range of X and Y coordinates with another color. Text is added on top by copying predetermined patterns of pixels for each letter or through some other algorithm. To display a window, it's necessary to know its specific width and height and the current position of its top left pixel. Adding the x value of the left pixel and the width by simple arithmetic gives the rightmost edge pixel. A title bar can then be drawn along with a border, text, and so on. If the user moves or resizes the window, all of this arithmetic has to be redone and the window redrawn. The simplest computer graphic involves drawing a line between 2 points, both with their own set of coordinates x, y. The Bresenham algorithm involves a loop which draws just such a line by following a straight xy curve, familiar from school mathematics. Draw 3 lines and you have a triangle which can be filled with textures, illuminated by simulated light sources and combined with thousands of others to make a 3D shape. No matter how complicated, it all comes down to addition, multiplication, and jump instructions compiled into functions. Sound is the other major form of output from a computer. Sounds are waves of high and low pressure moving through the air. Speakers and headphones produce sounds by moving a membrane back and forth. There is a permanent magnet attached to the membrane inside a fixed conducting coil. An oscillating current through the coil pulls the magnet in and out, making the membrane oscillate and creating a sound. The computer breaks up time into short steps and specifies the current at every step in time by sending a binary number to a sound card. Electronics turn the digital binary values into the appropriate current. A microphone works in exactly the opposite way. There are many input devices out there, but the way a computer deals with inputs is usually the same. The inputs leave so-called messages in memory, which are groups of bytes of preset length identifying the device and what exactly the input consists of. For example, a message queue may have in it 3 messages of 8 bytes each. When decoded, the first one states that the A key has been pressed down, the second states that the mouse has moved 30 pixels to the right, and the third that the shift key has been released. On a keyboard, the keys are arranged into a grid. When a key is pressed, it makes an electrical contact between a horizontal and vertical row, allowing the precise key to be identified. Between the keyboard and the computer's motherboard, the message announcing when a key is pressed down or released is relayed to computer memory, allowing the computer to act on it. In our video game example, imagine that the B button is used to buy things and the S button is used to sell. In Windows, these key presses have corresponding decimal numbers 66 and 83 respectively. In terms of instructions, the game would have conditional jumps based on the value of the last keystroke. If the keystroke value is 66, then the computer would jump to a set of instructions corresponding to buy. If 83, it would jump to instructions corresponding to sell. A computer mouse tracks how far left or right and up or down it has moved along a flat surface, and also which buttons have been pressed. A program, typically the computer's operating system, keeps track of the X and Y pixel coordinates of the mouse by adding or subtracting any changes in position received from the mouse. Say that a window with a button is currently active when a user presses down the left mouse button. The program will check the x-coordinate of the mouse cursor against the dimensions of the button. If x is greater or equal to the left side of the button and less than or equal to the right side of the button, then the click is horizontally inside the button. The program must then check the y-coordinate is vertically inside the button too. If both are true, the button is considered pressed. If at any moment you have 10 buttons on screen, the program will check every button in turn if it's been pressed down or not. To summarize, a computer display is a grid of pixels, each one a group of a red, a green, and a blue light. The brightness of each light is set by a corresponding byte in computer memory. A pixel, therefore, has an arbitrary color, and a group of them together makes an image. Sound is recorded by measuring the motion of sound waves and saving them as binary numbers in memory. The reverse process is used to play back the sounds. External devices send messages to the computer which are placed into memory, allowing the computer to identify inputs, such as when a key has been pressed or the mouse has been moved, and then act upon them. Finally, I want to take stock of the entire video. I think it's amazing how doping silicon with impurity elements and performing relatively simple logical operations allow us to watch and create videos, process information, and even inhabit virtual worlds. Computing is all about building up simpler concepts to achieve more complicated ones. If you've got CMOS pairs, you can make a NAND gate. If you've got NAND gates, you can make any logic gate. If you have logic gates, you can make instructions. If you have instructions, you can make algorithms into functions. From functions, you can build up programs as complicated as you like. This also means that computers are very dumb. They have no intuition and must rigidly follow programs which have every possible eventuality spelled out in great detail. In this video, I will give a basic overview of how optics work and answer questions such as: why does your phone camera need a lens to take an image? Why do some people need glasses? The world around us is filled with light from a spectrum of colors. When a ray of light of a certain color traveling in a straight line hits a photodetector, its position and color are registered. What I'm calling a detector could be cells in your eye or photographic paper, but for now I will talk about the kind of detector you have in your cell phone or webcam. Just as the screen you're looking at now is made up of individual pixels emitting light, the detector in a digital camera is made up of a grid of pixels which can sense light. Alice takes a detector when she goes out and then sees a strange sort of traffic light with a red light bulb at the top and a blue bulb below it. Alice holds the detector up to take an image of the lights. The image will be an accurate representation of the real world if the top pixels are red, then there's a gap, and then the bottom pixels are blue. In reality though, light spreads out in front of both the red and blue bulbs and illuminates all of the pixels at once. Every pixel is equally red and blue, so the image appears to be all purple. This is why we need an optic to focus light. I will go into more detail on what it means to be in focus later on in the video, but for now, think of it as when the red and blue light go to separate points on the detector so that an image has the two bulbs separated rather than just be completely washed out with purple. The simplest solution to this problem is to put a box around Alice's detector to block out stray light and put just a tiny hole, often called a pinhole, in front of the detector. The pinhole blocks out all but one of the red and one of the blue rays of light so that they fall on different parts of the detector. The bulbs are separated in the image, which is exactly what we wanted. The image has become inverted because light from the bottom blue bulb has gone to the top and vice versa. But that's okay, this actually happens with most optics. We can always use the computer to invert it back or wire up the detector to take account of this inversion. Your brain has naturally adapted to compensate for this effect in your eye. This type of darkened box with a pinhole is one of the first optical tools to be used to actually record images. The modern word camera comes from the Latin phrase camera obscura, or dark chamber. Here is an 18th century illustration of a camera obscura with a pinhole. The pinhole camera illustrates the two main properties every optic must have. If the pinhole is large, too many rays get in from each of the bulbs, and eventually it is as if we are back at the start, with no optic at all. If we make the pinhole smaller and smaller, the amount of light getting in decreases, and the image will become darker until it fades completely. The problem with a pinhole camera, therefore, is that it is a trade-off between how much light gets to the detector to actually create the image, often referred to as the size of an optic's aperture, and the degree to which the direction of the rays is restricted. This is the resolution of the optic, which I will mention later. Ideally, we would want plenty of both. Other optics consist of mirrors, which reflect the sources of light onto the detector. With a plane mirror, as you might have in your bathroom, light reflects the same way as a ball bouncing off a wall in a game of squash. How a ray of light is reflected depends on its direction, with the angle of incidence equal to the angle of reflection, relative to a line pointing out of the mirror called the normal. On its own, a plane mirror won't help us avoid the problem of the two bulbs turning the whole detector purple we saw earlier. Instead, the mirror must be curved either into a part of a sphere or into a special shape called a parabola. What this shape of mirror means is that when rays from the two bulbs come in, and they do so at different angles, they are reflected to different parts of the detector. In fact, all the blue rays go to one part and all the red ones to another. Just as with the pinhole, the image is inverted, but light from the two bulbs goes to separate parts of the detector as required. This setup solves the main problem of the pinhole, because you can make the mirror as large as you like in principle, and therefore collect plenty of light while still forming a clear image. However, the main disadvantage of this type of optic is that it's cumbersome and very long, due in part to the light being reflected back on itself. For this reason, this setup is mainly used for telescopes. The telescope tube forms the dark chamber to block out stray light, and usually a second plain mirror is added just to divert away the light to the detector. The first known working mirror telescope was made by Isaac Newton, and more recently the Hubble Space Telescope used a similar but slightly more complicated arrangement. This brings me on to lenses, a type of optic which uses refraction. Imagine that you have a truck running on a hard road and suddenly it hits the edge of a muddy field at an angle. For a moment, only one of its tires is on the mud, so one side of the truck slows down while the other continues at speed. The truck turns. In a similar way, light bends or refracts into a dense material like glass, and refracts in the opposite direction when it transitions from glass to air. With a rectangular glass block, the light enters and leaves going in the same direction, just shifted slightly. Having the two opposite sides inclined alters the direction of the emerging ray in proportion to the slanting. By curving the shape of the glass in a similar manner to the curved mirror from before, rays of red and blue light will likewise be diverted to different parts of the detector. Just like with the mirror, a lens can be made larger to admit more light while still maintaining a crisp image. The advantage of the lens is that it allows a practical and compact optical device, such as the human eye or a cell phone camera. The lens is at the front to focus light, there is a chamber to block any stray light, and the detector is at the back. This makes the lens into the most ubiquitous and important type of optic. Usually a high-level optics textbook or a class would talk about what happens to a single point of light. They talk about things like the point spread function of an optic, the pattern of light that a point source produces on a detector. This is because we can always take objects, things in the real world which are sources of light, and break them up into a large amount of individual point sources. As long as the optic works on just one such point, it will also work for any number of others which make up a whole macroscopic object. For an optic to focus light then is to take in a number of the rays that diverge from a point source in all directions and to redirect them using reflection, refraction, or other ways I haven't mentioned to a single pixel on our detector. I will talk only about lenses from now on, but the same arguments apply to other optics like the Newtonian telescope I mentioned. Based upon their shape and other properties, every lens has a so-called focal length. When the point source you're observing is very far away, almost infinitely far away in fact, then this is the precise distance behind the lens that the rays converge and the light is focused. This is therefore the precise distance at which to place the detector behind the lens. If you put the detector too close, then the rays of light haven't yet converged on a single point. If you put the detector too far from the lens, the rays have begun to diverge again. Both cases show what it means to be out of focus. Each point of light now spills over multiple pixels and the whole image becomes blurry, as you can simulate with the blur tool in many image editing programs. The closer the point source comes to the lens, the further the focus moves behind the lens. There is a precise mathematical relationship between the focal length, the distance from the object to the lens, and the distance to the resulting focus. This shifting of the focus is a problem if you have just set up your detector exactly one focal length behind the lens to image things in the far distance, and now want to image a closer object. Cameras and eyes overcome this issue in two particular ways. When taking a photograph with a camera, once the object to be focused on has been selected, the lens will be moved by the photographer or automatically by the internal circuitry of the camera to pick the right distance between it and the detector. The size of the human eye is fixed, so instead muscles change the shape of the lens and therefore its focal length to shift the focus backwards or forwards as required. In this way, the light-sensitive cells in a layer called the retina, which is the detector in your eye, can stay where they are. Try to hold a pencil close to your face. You can either choose to focus on the pencil, in which case the background goes blurry, or vice versa. Either way, your brain is automatically using muscles to stretch or compress the lens in your eye to achieve the correct focal length to focus on what you want. As I've just explained, if an object is far away, then light is focused close to the lens. For some people, no matter how much their muscles try to adjust the lens, they can never shift the focus of a distant object backwards far enough onto the retina, and they are nearsighted. Conversely, when objects are close, some people can never quite manage to shift the focal point far enough forward, and they are farsighted. Glasses or contact lenses can correct for these problems. In the far-sighted example, the problem was that rays of light were diverging too strongly from a nearby object, but an additional lens can bend the rays inwards as if they were coming from a distant object. For nearsighted people, the lens makes rays diverge as if the object were closer. Other optical instruments like binoculars also bend the direction of rays using a combination of lenses to make objects appear as if they are closer and therefore more magnified. No optic is perfect, and therefore rays of light are never totally focused. Pixels in digital cameras are small and getting smaller, but an infinitesimally tiny point of light will always appear to have at least the size of a pixel. Both of these effects together mean that two separate points of light, if they are close enough together, will appear to merge into a single point. The resolution of an optical instrument is a measure of how close together they can get before they can no longer be distinguished. Thinking of objects as collections of many point sources, the resolution determines how sharp features in the image will be, or how small or far away an object can be before it blends into the background. One thing to keep in mind is that most objects do not give off light themselves, but merely reflect it. All matter reflects light to some extent. What you might think of as reflection, seeing a light bulb reflected in a plane mirror for instance, is technically called specular reflection. The mirror is polished to a smooth surface so that the rays neatly preserve their order, whereas reflection from a brick wall is called diffuse reflection because the roughness of brick scatters and jumbles up rays from the bulb and from other objects in the room. Also, unlike the mirror, the brick preferentially absorbs some colors, allowing ones like brown to be reflected. Thank you for listening. If you are interested in how a computer works, stores information, and displays images, there should be a link on the screen now. If you have any questions about optics or any other topics for me to cover, please leave a comment. I did not cover advanced topics such as diffractive optics like Fresnel zone plates, nonlinear optics, or optical fibers. I can make follow-up videos if there is enough interest. In a lot of science fiction, humans boldly go to faraway stars and planets without much of a second thought. The heroes are able to cover astronomical distances using fictional hyperdrives or teleporters, whereas in reality the speed of light is known to be the ultimate speed limit in the universe. Even at this limit, interstellar journeys would be long. Stars are separated by multiple light years, 1 light year being the distance light travels in a year. People have speculated about how long a more realistic journey would take without any sci-fi technobabble. It's rare, though, to find a discussion within popular media which is actually motivated by robust knowledge of physics and relativity. One argument goes as follows. With current spacecraft technologies, it would take thousands of years to reach the nearest star. This means that many generations of people would be born and die during the trip. What is more, it would seem likely that a new, faster spaceship capable of overtaking the original would eventually be constructed, rendering it obsolete. This would make interstellar travel unattractive for the astronauts and for society as a whole. I believe that such a generation ship would be impractical, and in this video I will explain why a crew could make the trip in their lifetimes and ensure that they are not overtaken in reaching their goal. You are probably watching this on or near the surface of planet Earth, where gravity is pulling you towards the center of the planet. Unless you are a skydiver or an oligarch who has accidentally fallen out of a window, there is a floor beneath you exerting the same force upwards. You are pinned to the floor by the force of gravity. If the floor wasn't there to stop you falling and there was no air resistance, the force of gravity would be enough to accelerate you downwards at a rate of 1 g. You might have accelerated even more rapidly than this in a fast car, roller coaster, or aircraft if you were said to have pulled a lot of G's. One of the postulates of general relativity effectively states that gravity and acceleration are indistinguishable. Being pressed into the surface of a planet by gravity is the same as being pressed down to the bottom of a spaceship accelerating at a corresponding rate, even if it is far away from any sources of gravity. This makes 1g a pretty good rate of acceleration if you're an astronaut on board a spaceship. While accelerating or decelerating, the astronauts would experience the equivalent of Earth gravity. No weightlessness, no muscle loss, and so on. With a much larger acceleration lasting for an extended period of days or more, the human body may not survive such harsh stresses. With a much gentler acceleration, you would never get anywhere. Mathematically, an acceleration of 1g means increasing your speed by 10 meters per second every second, or going from 0 to 36 kilometers per hour in 1 second. So for example, after 1 second, your speed would be 10 meters per second, 20 meters per second after 2, and so on. If you did so for long enough, it would seem that eventually you would exceed the speed of light. But there's a catch in the form of Einstein's special theory of relativity. One of its postulates is that the speed of light is the same for all observers. This is actually very strange. Imagine if Alice flashes a laser beam which moves away from her at the speed of light, while Bob is on a spaceship going at half the speed of light in the same direction. Surely Bob must perceive the beam as escaping from him at only half the speed of light again. Well, no, because as the postulate states, the speed of light is the same for both Alice and Bob. The way to reconcile these facts is that Alice and Bob perceive time and space differently. One consequence is that even when an object is experiencing what it feels as a constant rate of acceleration, for example if a spaceship's engines are putting out a constant amount of thrust, it will never quite reach the speed of light. So there are two ways to view an interstellar spaceship. Mission Control on Earth sees it moving away and getting faster, but as the spaceship approaches the speed of light, the speed levels off. Eventually, the engines cut out and it recedes at a constant speed. Astronauts on board are pretty much stationary relative to the spaceship, but they feel 1g, just like you are right now, until the engines cut out and they feel weightless. Star systems move at tiny speeds compared to what we're discussing here, so I will treat them as near enough stationary relative to each other. This means that a spacecraft must spend just as long decelerating to a stop at the end of the voyage. A typical trip would look like this. Burn forward for a certain time so your speed rises, but never gets to the speed of light, then coast along at this constant speed, and then burn back to come to a stop again. A small amount of distance will be covered during the speed-up portion, an equal amount during the slowing down portion, but most of the interstellar distance is covered during the high-speed coast phase. The Alpha Centauri system, actually consisting of 3 stars, is the closest to Earth at 4.4 light-years. Suppose that a spaceship maintained a rate of acceleration of 1g for an entire year. As a result, the spaceship would be traveling at just over 70% of the speed of light. Factoring in the acceleration and deceleration stages and the final speed, the spaceship would take just under 7 years to make the journey from the perspective of the Earth. This is a pretty reasonable time frame, shorter than many prison sentences. In fact, due to time dilation from traveling close to the speed of light, the astronauts get time off for good behavior. The trip appears to last only about 5 years to them. More on this in a moment. If the ship had enough fuel to only accelerate and then decelerate for half a year each, the trip would take 11 years from Earth's perspective and 9 years from the cruise. Still not too bad. What about somewhere further away like the 82 Eridani system? It's 20 light years away, meaning that even at the speed of light, the trip would take 20 years. For this journey, I would recommend an acceleration time of 3 years to reach 95% of the speed of light. At this speed, time passes over 3 times slower for the spaceship relative to the Earth. In other words, suppose the astronauts decided to have a baby during the trip. This obviously takes 9 months from their point of view, but during the same period, people on Earth would have held 3 annual Oscars ceremonies, which might actually be a downside for the poor kid. The whole trip takes 22 years from Earth's perspective, but only 8.5 for the astronauts. As an aside, once a ship has departed Earth in these scenarios, it will almost certainly not be overtaken or beaten to its destination. With a travel time of under 7 years to Alpha Centauri as seen from Earth's perspective, A follow-up mission could beat it by 3 years at most if technology to travel at light speed was somehow invented. Even if instantaneous teleportation technology were invented the day after they left, the astronauts would still arrive at their destination first. Their 7 years travel time is roughly equal to what I will call 1 unit of DAT, or Denver Airport time. The time from when the city of Denver, Colorado made a preliminary agreement to acquire land to an airport becoming operational. It's also about half a BAT, or Berlin Airport time. Even in the future, large projects will take time to complete, will suffer delays and require bureaucracy. In any case, based on the numbers, I believe that the main necessary and sufficient condition for humans to go interstellar is to have a spaceship which can accelerate at a rate of 1g for a total of around 1 or 2 years. This is of course much easier said than done, and we are nowhere near the technology to make this happen, but let's have a look at how such a feat might conceivably be accomplished within the known laws of physics. Maintaining 1g of acceleration is no big deal for a modern rocket. In fact, higher accelerations are routine. The problem is that they only have enough fuel for a few minutes of burn, not for a couple of years. Getting a simple chemical rocket with enough fuel to make an interstellar trip is a problem for the following reason. An ordinary rocket is propelled forward when hot gases shoot out of its engines at high speeds. Every action has an equal and opposite reaction. So the larger the momentum or inertia of the gases going backwards, the more momentum the rocket builds up going forward. Suppose we have a 1 kilogram satellite and we need 1 kilogram of fuel for its final 1 minute burn forwards. What about a 1 minute burn before then? We would need 2 kilograms of fuel, 1 more for the satellite and 1 for the first bit of fuel. We need 4 kilograms for the minute before that, 8 before that, and so on. The amount of fuel required grows exponentially with the amount of time the rocket accelerates for, like the grains of rice on a chessboard. In other words, we need to propel the fuel, to finally propel the satellite. This is why rockets are normally staged. A small spacecraft final stage sits on top of a large second stage, which in turn sits on top of a huge first stage. To have enough of our current fuels to keep burning forward for years, the stages would get absurdly large. But there is hope. Let's say that we have a super advanced fuel which gives twice the impulse or kick from the same amount of ordinary fuel in the example I gave previously. This means we only need half a kilogram for the final minute of burn, 3/4 for the last but 1 minute, and so on. So although the fuel is only twice as good as before, the final mass of the rocket is also exponentially smaller. What we want then is a fuel which shoots out of the back of the spacecraft's engines carrying the most possible momentum, because this will give the spacecraft the largest possible push forward. Fortunately, due to relativity again, there is no limit to how much momentum any given piece of matter, such as a grain of sand, a molecule, or a particle, can carry. You could, in principle at least, accelerate a huge spaceship to half the speed of light by firing out just a single atom with an eye-wateringly large amount of momentum. Granted, I can't imagine a technology which would get the job done with just one atom, but we could certainly greatly increase the amount of momentum every piece of propellant carries over current chemical rockets. One place where a large amount of energy, and therefore momentum, is imparted onto matter is a particle accelerator. A big machine, such as the Large Hadron Collider at CERN, can impart 6.8 trillion electron volts of energy onto a proton, which corresponds to a huge amount of momentum. Even with advanced technology, it would probably be impractical to blast the city-sized LHC into space to use it as a rocket engine. However, let's assume that it would be possible to make a particle accelerator which can reach about 1 billion electron volts into a spaceship engine. Now, if you aren't familiar with what this unit of energy means, it doesn't really matter. But to sum up, we want our rocket fuel to have as much energy as possible. The most energy humans have ever given to a piece of fuel, or a piece of anything, is 6.8 trillion in units of electron volts. And I'm suggesting we get a rocket engine which goes to just 1 billion. There are technologies such as laser Wakefield accelerators, where particles can reach these energies in a few centimeters of space on top of a laboratory bench. So it's not inconceivable that corresponding space thrusters can be constructed which are small and light enough to be practical. With all this in mind, the ship would have to bring 1.8 units of propellant for every unit of actual ship mass for the 7-year trip to Alpha Centauri. Let's say the mass of the spaceship, the astronauts, life support, whatever equipment they would need at their destination to establish a permanent base, would be 200 or so times the International Space Station at 100,000 metric tons. There would need to be 180,000 tons of propellant. All that's important is how much more fuel is required relative to the spaceship mass. If Private Pyle wants to bring an extra kilo of donuts on the mission, there would need to be 1.8 more kilos of fuel, and so on. So far, this isn't looking too bad from a practical point of view. Note that just as with rocket stages, it's possible to store the propellant in individual tanks attached to the spaceship, which would detach after becoming empty, a bit like the external tank on the old space shuttles. This just means that the mass of the fuel tanks themselves need not be included in the final spaceship mass. While we have the basic technology for the ship's engines, the issue of powering those engines is much harder. The energy itself requires a mass of fuel. That is what Einstein's famous equation E=mc² means. The most energy that can be extracted from a parcel of matter is its mass times the speed of light squared. And that's just the theoretical maximum. Burning releases less than 1/millionth of this amount, while nuclear reactions release a fraction of 1%. The less efficiently we can extract energy, the more massive the spaceship gets, which in turn means we need to bring more fuel and so on. One sure way to get to the theoretical maximum is to annihilate matter together with an equal amount of antimatter. 1/2 kilogram of each would release the speed of light squared's worth of energy. Antimatter has been generated on Earth, so we know it can be done in principle. We are just nowhere near manufacturing it in any significant quantity. There are also huge unknown technological issues with storing antimatter and then efficiently using the energy that comes out of it. I have seen other proposals, such as taking a miniature black hole, which is even more technologically uncertain. So in short, storing energy close to the theoretical maximum is at the very early lab stages of development, with perhaps centuries of development ahead. Remember that I ran calculations with each proton having 1 GeV or 1 billion electron volts of kinetic energy? This is significant because it means that one proton is carrying the energy equivalent of a second one. So for every kilogram of propellant which will be shot out of the back of the spaceship, about 1 kilogram of fuel must be turned into energy. Something like a total inventory of 1.5 kilos of hydrogen and 1/2 kilo of antihydrogen. This makes the propellant overall half as efficient per unit mass as before, and this in turn means a more than doubling of the mass of fuel required. In fact, the Alpha Centauri mission would need over 7 kilograms of mass of this propellant fuel mixture for every 1 kilogram of spaceship. And all that is assuming a perfect theoretical efficiency. So I would argue that it might be doable, but certainly difficult and expensive. Another possibility is called a photon rocket, where matter and antimatter annihilate to produce gamma rays. It is then those gamma rays, moving at the speed of light, which fire out of the back of the spaceship to propel it forward. The gamma rays come out in pairs, and at least one of them needs to be redirected for this to work, which is extremely challenging technologically. At perfect efficiency, this would require 5 kilograms of fuel for every kilogram of spaceship. Half is matter and the other half antimatter. In both cases, there are other tricks to make the journey more tractable, such as somehow beaming energy from Earth or from some automated installation in deep space. Imagine, for example, a scenario where a second, slower and fully automated ship full of fuel is sent out ahead of the main ship, crewed by people. The crewed ship doesn't have enough fuel to fully decelerate upon reaching Alpha Centauri. However, the two missions are perfectly timed, so that just as the crewed ship runs out of what fuel it does have left, it meets the robot ship and completes the deceleration. You could repeat the idea of staging by then sending out 2 more fuel ships, another one for the colony ship and another one for the first fuel ship, and so on and so forth. Also remember that dumb canisters of fuel or even robotic spacecraft are not limited to a few G of acceleration like living beings. It's possible to fire a beam of individual fuel atoms, possibly antimatter, out of a particle accelerator, or guided canisters out of a long electromagnetic railgun. Things like cannons or railguns involve skull-shattering levels of acceleration, but are much more efficient than rockets, because they don't have the exponential fuel-to-push-fuel kind of problem. Although it would require advanced technology and lots of resources, I believe it's possible to complete an interstellar trip taking a fraction of a human lifetime within the boundaries of known physics. To summarize, squishy humans on board an interstellar ship are limited to accelerate at a rate of about 1 g, which is the same rate that a falling apple would accelerate due to the Earth's gravity. If the ship can maintain that rate for something like a year, remembering that you have to spend just as long decelerating at the end, then it can get to a good fraction of the speed of light. This would complete a journey to the nearest stars quickly enough that the original astronauts would be young enough to set up a colony and have kids. This is also helped by the fact that time dilation would make the journey appear to go quicker for the astronauts. To make that happen, however, you would need technology far beyond what we have available. In particular, the engines would have to be very efficient in terms of firing propellant out of the back of the spaceship, while the power source for them would have to be extremely energy dense. I will put up the relativistic equations on screen and answer questions in the comments. Thank you for watching.
Johnny, I want to do a serious commercial for once.
Well, you're not off to a great start with a plastic crown on the cake.
Seriously, people need to know that we carry the best brands like Helix, Nectar, Brooklyn Bedding, and others.
You just told them.
They should know about our fast one-day delivery and 100-night comfort guarantee.
They do now.
And they should know that adjustable bases start as low as $350.
Yes, and they should know your fly's been open this whole time.
It had seen planets crumble and stars ignite. It had skimmed supermassive black holes and galaxy-destroying quasar jets. It had crossed light years of nothingness and caught a glimmer of the edge of the universe. And now, more than 4 billion years after its epic journey had begun, the probe had returned home. The sun was a swollen red giant, grotesque and violent. Mercury and Venus were gone. Earth, such as it was, survived, but only as a tattered lump of iron and nickel orbiting dangerously close to the dying star. Humanity, barely 100 million in total, had found a new home on Europa. The heat from the red sun had melted its ices long ago, and now the little moon of Jupiter was the only sanctuary they could reach. It took the probe several minutes to decipher the strange language of the radio signals they sent. It seemed the remaining humans were abuzz with curiosity, tinged with hope. They remembered the probe, even though it had been launched so long ago, memory of the event miraculously preserved through the ages. Humanity, they said, had tried and tried again to spread amongst the galaxy, but every attempt at a colony had failed. They could send machines out into interstellar space, but every time they had attempted the crossing for themselves of the great void between the stars, their frail bodies had failed them. As far as the humans knew, they were all that was left. And as the beating red sun at the heart of their solar system constantly reminded them, they were running out of time. But they also knew that long ago, interstellar spacecraft like the returning probe had been created, fashioned with artificial intelligence as keen and sharp as any biological brain, to go forth into the galaxy and the greatness beyond. These probes had been tasked with cataloguing everything, yielding the history and secrets of the universe in a way that no mere telescope ever could. From the relative proximity of the inner solar system to the most distant, alien and bizarre things in the cosmos, the probes had been told to see it all. The largest, the most powerful, the weirdest, all of it. And all of this searching, all of this cataloguing, all of this measuring was to be in service of a greater goal. To find a way for humanity to travel beyond the solar system. Over the unfathomable ages, millions of spacecraft had been sent, but only one had returned. And so, fulfilling its promised mission to its long-dead creators, the lonely probe began to tell its multi-billion-year story, relating what it had learnt, the extraordinary events it had encountered, the remarkable places it had been. It began to describe everything within the universe. There are parts of the universe that are impossible to film. From quantum particles to spectacular distant quasars, sometimes it's a struggle to pull together visuals that help show what we are describing. But Storyblocks has been a big help. Not only do they have great space footage and colourful imagery to help represent the microscopic world, they also help us show places we don't have the budget to go. Dropped your drone in a lake? Should have used Storyblocks. Wasted time on getting footage that didn't make the cut? Should have used Storyblocks. Storyblocks' curated stock library has everything you need to create high-quality video in one place, with unlimited downloads and over 1 million 4K or HD footage, templates, music, sound effects, images, and more, all for one predictable subscription cost. As well as this, anything you download with Storyblocks is 100% royalty-free and will stay protected in perpetuity by the highest level of legal coverage in the industry. They also have the best motion library on the market, refreshed frequently, and you can save time by accessing Storyblocks' entire stock library in Premiere Pro and After Effects by using the Storyblocks plugin for Adobe Creative Cloud. So, to get started with unlimited stock media downloads at one set price, head over to storyblocks.com/history of the universe, or click the link in the description. Mission Parameter 1. Search for signs of life outside the solar system. The probe had called itself Batuta. It had taken the name from the great 14th century explorer Ibn Battuta, who had travelled over the course of 3 decades across the entire known Muslim world, in his lifetime covering almost 117,000 kilometres and handily beating out other great explorers such as Marco Polo and Zheng He. The spacecraft knew that such a name would be fitting as it ventured out into the seemingly endless black. But before it could begin its journey beyond the solar system, it had to pass a series of tests. It had 1,000 siblings, each one as smart and capable as itself, but only a select few would be granted the privilege of fully independent thought and autonomous action outside of any human control. Those who failed would be stuck forever inside the solar system. Batuta had to show its human creators that it could survive the harsh conditions it would face in the wider universe, and that it could concoct clever experiments to divine nature's most closely held secrets. And so it began its trials on Titan, the largest of Saturn's moons, and one holding remarkable secrets. Secrets uncovered by a probe just like Batuta, many millennia before. Titan was discovered by humanity in 1655, when pioneering astronomer Christian Huygens spotted it with his homemade telescope. Huygens himself was a key figure in the evolving scientific revolution, and was also the first to attempt to scientifically explore the possibility of life on other worlds, writing, "Some planets indeed might be capable of accommodating several species of rational creatures possessed of different degrees of reason and sense." But little did Huygens know that Titan itself would be a candidate. And it was on that moon that centuries later humanity achieved a great milestone of space exploration. In 2005, A small probe, not even 3 meters wide, broke free from its attachment harness on the left side of the Cassini spacecraft that had spent nearly 7 years in its journey to Saturn. And it took the probe a further 22 days to coast from Cassini's orbit to Titan. This craft, named after Huygens, used a parachute to slow its descent through Titan's atmosphere, this only working because among all the worlds in the solar system, Titan is the only place besides Earth and Venus to host a significant atmosphere surrounding a rocky body. Huygens landed gently, making a dent in the icy surface before bouncing and sliding to a stop. The first time that an emissary of humanity had touched the surface of a world in the outer solar system. For Batuta, Huygens was a true pioneer. And indeed, the world it touched down on was unlike anything else that humanity had ever encountered. "50% larger than Earth's moon and 80% more massive, Titan is appropriately named. Its core is mainly rock, but its crust is made of ice. Surrounding that is a dense, thick atmosphere, even denser than the Earth's, giving it an atmospheric pressure on the surface about 50% greater. Titan is a beautiful, ghostly, and enigmatic world, because it shares one thing in common with the Earth that all other worlds in the solar system lack: liquid. Titan has rivers, streams, estuaries, deltas, and every other feature associated with surface liquids. You can stand on the shores of a lake, its shimmering surface stretching beyond the horizon, feeling the gritty sand beneath your feet as waves lap at your ankles. And all of this at a temperature almost 200 degrees Celsius, below zero. And so the lake stretching out before you isn't one of water, but one of hydrocarbons. The rain falling from the sky isn't water droplets, but one component of a cycle that evaporates hydrocarbons like methane and ethane up into the atmosphere and precipitates them back down to the surface. But kilometers beneath your feet, through the ice crust that makes up the outermost shell of the moon, there is a liquid water ocean, warmed by internal heat and kept liquid through the presence of ammonia. Indeed, Titan is the only known world with liquid both on and underneath its surface, which makes it a tantalizing home for two kinds of alien life. First, the familiar, something that every organism on Earth shares, the use of water as a solvent. Water is the container in which life operates. It allows for molecules to mix and recombine, it allows for temperature regulation, it brings food closer and eliminates waste, and it helps cells maintain their shapes. But water is not the only liquid. The shallow seas and lakes and streams of hydrocarbons on Titan could serve a similar function. Ethane and methane acting as solvents for a strange sort of biochemistry operating 200 degrees below zero.
Grainger makes it easy to find and order the products your team depends on around the clock. Because when boxes are packed, pallets are stacked, and trucks are waiting at the dock, the last thing you want is to run short on the supplies that keep your warehouse moving. Grainger is there to help make sure nothing runs out when shipments are rolling out. Call 1-800-GRAINGER, click Grainger.com, or just stop by. Grainger, for the ones who get it done.
And Titan is not alone when it comes to enigmatic underground oceans. Enceladus, a tiny moon of Saturn only 500 kilometers across, also hosts large oceans. Europa, Callisto, and Ganymede of Jupiter all likely contain more liquid water than the Earth does. Even Pluto, clinging to scraps of internal warmth from radioactive decay in its core, might host a subsurface ocean. However, reaching these oceans is no easy feat. At the temperatures of the outer solar system, far from the light and warmth of the sun, water ice is hard as rock, ensuring that worlds like Europa and whatever secrets may inhabit those dark, world-girdling oceans are encased in ice sheets over 100 kilometers thick. Upcoming missions, such as the European Space Agency's JUICE, short for Jupiter Icy Moons Explorer, and NASA's Europa Clipper, will not attempt to pierce the icy shells of these worlds. Instead, they will orbit and, if conditions are right, swim through the plumes of cryovolcanoes. For the icy moons like Europa are not sterile and still, but active and alive. Their crusts creak and groan as gigantic fields of ice grind against each other, a colder, slower version of the tectonic activity on Earth. If there is any biological activity in those mysterious oceans, the plumes of these frozen volcanoes may carry molecular signs of it. If enough elements can find themselves in sufficient concentrations, life may yet find a way in those lightless oceans. And those are not the only mysterious interiors to be found in the outer solar system. The Huygens probe transmitted 90 minutes of data back from the surface of Titan to the Cassini spacecraft, before Cassini moved out of range and the signal was finally lost. However, the tiny probe was designed to withstand the environment on the moon's surface, so most likely remains intact today, a lonely human monument on an alien world. But before its daring mission on Titan, Cassini by itself had already captured many spectacular images of the outer planets, including a stunning colour image of Jupiter's Great Red Spot, exactly 335 years after it was first discovered by the scientist, after which the spacecraft got its name. Contrasting with the close companionship of their namesake pioneering probes, Giovanni Cassini and Christian Huygens were not exactly the best of friends during their time together in France. A few years after Cassini's arrival in Paris, Huygens remarked to his brother Constantine that Cassini was at the telescope every clear night, and that Huygens would never want to do that, being satisfied with his earlier astronomical discoveries, which, at any rate, were much more important than those of Cassini. And yet, despite Huygens' protestations, Cassini's commitment and methodical process would yield remarkable results. For example, Jupiter's Great Red Spot. This spot is a magnificent storm, a hurricane with wind speed of over 400 kilometers per hour that has been raging for centuries. At its largest known extent, it could have swallowed the entire Earth 3 times over, although it's slightly smaller in the present day. But interestingly, recent studies of the measurements taken by Cassini in 1665 have actually shown that it may not be the same storm seen 400 years ago. It may be a distinct new storm, less than 200 years old. Though iconic, it is clearly far from a permanent feature. This storm is not powered from the heat of the Sun, but from the interior of Jupiter itself. Indeed, Jupiter releases more heat into space than it acquires from the Sun, the result of a process known as the Kelvin-Helmholtz mechanism. Essentially, this mechanism is a leftover byproduct of the formation of the giant planet billions of years ago. As the planet cools off, it slightly shrinks, but as it shrinks, it compresses, heating it up. That heat can only be released into space through its surface to allow the shrinking to continue. Since Jupiter is so gigantic, it has an enormous amount of volume compared to its surface area, allowing the planet to stay warm for billions of years to come. Jupiter's Great Red Spot is not the only violent storm in the solar system. While backyard astronomers can easily track the Great Red Spot with even simple telescopes, we require more powerful instruments, and especially robotic probes, to see the rest. Cassini would go on to operate a further 12 years after the demise of its sister probe Huygens on Titan, before ending its life in a spectacular so-called grand finale, diving between Saturn and its rings in an effort to capture as much data as possible before flying straight into the planet. Its sacrifice deemed necessary as NASA scientists didn't want to risk polluting any of the moons of Saturn and their potentially habitable environments. And so on September the 15th, 2017, Cassini plunged into Saturn's atmosphere, its long journey of almost 20 years and 8 billion kilometers, coming to a dramatic end. But in those last years, without Huygens, it had managed to capture a revealing, eye-catching image of its final resting place. An almost perfect hexagon on the North Pole of Saturn. First spotted by the Voyager 1 spacecraft in 1981, despite its neat geometric appearance, the hexagon is not some alien relic. Instead, it's the result of the complex wind system in the upper Saturnian atmosphere. The winds in the atmosphere do not blow at the same speed at every latitude, and this triggers an instability that forms a series of cyclones in a ring surrounding the North Pole. And they all work together to form a gigantic vortex at the pole itself, like a ring of friends on a merry-go-round, all helping out to spin it as quickly as possible. Though seemingly enormous, storms like the Great Red Spot and the Hexagon are actually most likely relatively shallow, only a few hundred kilometers thick. Yet underneath those cyclones are surely more violent storms and much stronger winds, a never-ending maelstrom of intense forces and energies. Indeed, plunging through the atmosphere of a gas giant like Jupiter or Saturn would require a spacecraft that is well beyond the bounds of human engineering. But were we to be able to, we would encounter a truly bizarre sort of treasure. On the Earth, we usually encounter hydrogen as a gas. With enough effort, we are able to cool that gas to just 20 degrees above absolute zero, turning it into a liquid. But in 1935, the physicists Eugene Wigner and Hilliard Bell Huntington predicted that at extremely high pressures, hydrogen can exhibit some extremely strange behaviors. At a pressure of around 4 million atmospheres, that's 4 million times the pressure you experience at sea level, hydrogen atoms destabilize, with the protons forming a repeated lattice-like structure and the electrons free to roam amongst them. And this is exactly how we define the behavior of metals. And so at these pressures, hydrogen becomes metallic. When Wigner and Huntington first proposed this in 1935, it was just a matter of theoretical speculation. But it turns out that the interior of Jupiter has more than enough pressure to turn its bulk of hydrogen metallic. We don't yet know how deep this mantle of metallic hydrogen goes within Jupiter and Saturn's interior, but we suspect that it takes up the vast bulk of their volumes. In other words, most of Jupiter and Saturn are metallic hydrogen. And this means that since those giants are the largest planets in the solar system, most of the material of all the planets in the solar system is in a state completely inaccessible to our experience on Earth. And yet, as with the surface of Titan before it, daring space probes have been able to help us here, too. NASA's Juno mission, one of the next generation of probes to Cassini and Huygens and entirely solar-powered, was launched in 2011 and has carefully monitored the gravitational environment around Jupiter to paint a fuzzy picture of that planet's deep interior. It has found that it's very likely that Jupiter has no solid surface to speak of, just an inferno of gradually changing temperatures, pressures, densities, and compositions of matter.
At Walden University, we get the W. That's why we welcome and overcome challenges.
It's why our highlight reels are filled with lasting impact on our communities, on our families, and on ourselves.
We turn our passions into purpose, and we put in the work to earn it. Because we're here to create a legacy that elevates us
and everyone around us. Get the W.
Walden University, set a course for change. Visit waldenu.edu to learn more. Certified to operate by Chef.
And so, brutally strong magnetic fields and radiation, temperatures varying from almost absolute zero to tens of thousands of degrees, lakes of liquid methane, sheets of water ice 100 kilometers thick, exotic forms of hydrogen, and storms raging for centuries on end. But that was only a taste of the wonders and dangers that abound in the wider universe. For Batuta, this was just the beginning. It had spent the better part of a century navigating the trials of the outer solar system, devising schemes to drill through the icy outer layers of Europa, sending semi-autonomous probes into the metallic hydrogen inferno of Jupiter, skipping through the storms of Saturn, and more. And so after proving its worth, its ingenuity and its patience, Batuta had finally been permitted to exit the gates of the solar system in the full knowledge that the worst was yet to come. As it considered the sacrifices of the heroic probes that had come before it, the Cassini, the Huygens, the Juno, its curious mind turned to their predecessors, launched by NASA decades before, who had gone even further. Far beyond Jupiter, far beyond Saturn, far beyond the outer worlds altogether. For as strange and extreme as our own solar system is, we are not, by far, the strangest of systems out there. There are even weirder, more dangerous places. But to get to them, to explore their beauty and understand their secrets, Batuta would first have to travel the great gulfs between the stars. After only a few decades of cruising, Batuta had finally reached the long-established threshold. The heliopause, the boundary between the solar wind and the interstellar medium, a feat first achieved in ages past by the Voyager 1 probe in the opening years of the 21st century. Batuta could hear the ancient greetings etched in the famous Golden Record, a compilation of voices, languages, sounds, and music of planet Earth, hastily assembled in August 1977 just before the probe's launch by the legendary scientist and science communicator Carl Sagan and his collaborators. Indeed, the designers of this mission understood its significance. The probe would, decades after launch, become the first human-made craft to enter interstellar space. Musing on Sagan's words at the time, Batuta considered its own mission as it passed this remarkable milestone. Perhaps the records will never be intercepted. Perhaps no one in 5 billion years will ever come upon them. In 5 billion years, all human beings would have become extinct or evolved into other beings. None of our artifacts would have survived on Earth, the continents would have become unrecognizably altered or destroyed, and the evolution of the sun will have burned the Earth to a crisp or reduced it to a whirl of atoms. Far from home, untouched by these remote events, the Voyagers, bearing the memories of a world that is no more, will fly on. However, the mission had almost ended in disaster. Early in its journey, Voyager 1's scan platform jammed, removing the probe's ability to orient itself in space. Luckily, engineers were able to fix the issue by waggling the scan platform back and forth. But for years, during its outward cruise, they worried and fretted that all their efforts would be for naught. The mission, however, was a roaring success. Along with its twin, Voyager 2, humanity got its first close-up, high-res view of the outer planets, and that lonely probe, now long since lost to the infinite blackness of the space between the stars, was but the first of many. And it took advantage of a unique alignment in the solar system, when all the giant worlds happened to be all along roughly a straight line. By carefully arranging its trajectory in a trick known as the gravitational slingshot, the spacecraft was able to steal some of the momentum of the giants for itself, giving it more than enough speed to escape the sun's gravity permanently. After that, it was left to its own devices as it cruised through the galaxy, orbiting its center, just like every other star. But Batuta had other ideas. It was aimed in a general direction, but had not yet decided its first target. There were so many to choose from. Indeed, it had more than enough time to decide. The passage through the outskirts of the solar system would take several thousand years. and so Batuta busied itself with another task. It fashioned a thin metallic wire and unspooled it behind the spacecraft until it reached a length of 1,000 kilometers. It was a long, but simple, antenna. And through it, Batuta listened to the cosmos. It heard the groans of giant molecular clouds, the screams of stars torn apart by black holes, the subtle whirring of the Milky Way's magnetic field, the drumbeat of distant pulsars. Sometimes placid and sometimes riotous, it picked up a universal symphony, the perfect background music for the first leg of its journey. And it was through similar means that we knew when Voyager 1 had become the first ever human-made object to pass into interstellar space. For while the Sun's gravity extends for well over a light year, and objects still maintain feeble orbits at that distance, there really is a measurable distinction at the edge. And we know this because of the behavior of plasma. Normally we associate plasmas with dense, hot environments, like a bolt of lightning or the surface of the Sun. However, in the outer depths of the solar system, the plasma environment is still hot, but incredibly thin. And this plasma environment around the Sun is dominated by its solar wind. The entire solar system sits in a bath of these particles. But eventually, the solar wind slows down enough that it cannot sustain itself against the interstellar medium, and this supersonic flow comes to an abrupt and untidy halt. This boundary is known as the termination shock, and magnetic measurements from Voyager 1's antenna indicated that it encountered this boundary when it was at a distance of 94 astronomical units from the Sun, 1 astronomical unit being the equivalent of the distance from the Sun to the Earth. Past the termination shock is a region known as the heliosheath, where the solar wind slows down and begins mixing with the interstellar medium. And the outermost layer of that region, the border with true interstellar space, is the heliopause. Voyager 1 reached this boundary on August the 25th, 2012, at an incredible 18 billion kilometers from the Sun. And there it found that interstellar space is different. For the Sun's solar wind and giant magnetic field shield the solar system and its inhabitants from the toxic environment beyond. A toxicity brought about by the presence of deadly, interstellar cosmic rays. And to understand cosmic rays and what they mean for our survival on the Earth, we have to go back to 1912 and an Austrian physicist named Victor Hess. In the 19th century, scientists had discovered that air was seemingly being ionized by excess radiation. Radiation for which they simply couldn't pinpoint the source. It had been believed that this radiation had been coming from the Earth, from the ground beneath our feet. And so, measurements had been taking place at higher and higher altitudes to test this idea. Far exceeding the height of an experiment a couple of years before on top of the Eiffel Tower, Hess had used a hot air balloon to travel a kilometre up into the sky. He then followed this experiment by sending in his balloon to a height of 5 kilometres, but with one key difference. He performed his experiment during an eclipse. He saw no major difference in the quantity of radiation, both the Earth and Sun consequently eliminated as the cause. The results were clear and earned him a Nobel Prize in 1936. He had pinpointed a source of radiation coming from space. Just about every high-energy process in the universe creates cosmic rays. Some are created near the surface of the Sun, others come from distant supernovae, still others from quasars or magnetars or hypernovae. But because cosmic rays are charged particles, they can be deflected and reflected by magnetic fields. Thus our Sun provides a protective bubble around the entire solar system, and the Earth's field provides another line of defense for surface dwellers against these cosmic threats. But the defense is not total. High-energy particles encounter a typical human body roughly once every second. While most of them just harmlessly pass through, sometimes they strike a strand of DNA or oxidize a random molecule in a cell. If the damage done is left uncorrected, it can turn into a replication error, resulting in the growth of a cancer. Indeed, in 2023, Voyager 1 went silent for 5 months, possibly as a result of cosmic rays interacting with its computer.
PNC Bank brings you Call of the Wild Money Moves. Shh, listen.
Hey guys!
That's the sound of a multi-level marketing pitch.
This is life-changing, you guys.
Sounds like she wants you to buy lots of essential oils.
They are so essential.
And then have all your friends buy essential oils.
Are you more of a geranium or lavender fan?
Don't look her in the eyes.
Guard against wild money moves with PNC Bank. Brilliantly boring since 1865.
And these dangers get even worse beyond the heliopause, where not even the sun can offer its protection. But despite this, there are still objects here. Lonely denizens whose only knowledge of the sun is that of a prick of light, a star slightly brighter than the others. Young man, I'm afraid you are wasting your time. If there were any more planets, they would have been found long before this. In later years, astronomer Clyde Tombaugh would recall being told this in 1929, the year before he discovered Pluto. Pluto was at the time the most distant known object orbiting the Sun, and Tombaugh only saw it as a faint dot of light, betraying its existence as a planet only through its subtle movements against the background of stars. But over the decades, many astronomers hypothesized that Pluto was not alone, that there might be an entire population of objects, planet-sized and otherwise, in the fringes of the solar system. And it wasn't until 1992 that this hypothesis was confirmed, when a pair of astronomers, David Jewett and his graduate student-turned-collaborator Jane Liu, after half a decade of painstaking searches, found a companion to Pluto. The object would soon get a name, 15760 Albion, and it has since been joined by thousands of others in a population known as Trans-Neptunian Objects, TNOs, which stretch from roughly 30 astronomical units to an orbital distance of hundreds of thousands of astronomical units. This population, with subregions known as the Kuiper Belt and Scattered Disk, is the home of comets that make regular, frequent visits to the inner solar system, like the famous Halley's Comet. While these regions have a few larger members, Pluto, Sedna, Haumea, Makemake and others, the vast majority of trans-Neptunian objects are small objects made of frozen volatiles, like water, ammonia and nitrogen. Little is known today about the populations of the trans-Neptunian objects, but on January the 1st, 2019, we got our first detailed look at a smaller sibling of Pluto when NASA's New Horizons spacecraft slipped past Arakoth, a trans-Neptunian object only a few dozen kilometers across. Arakoth, which sits about 45 astronomical units from the Sun, is almost completely unlike anything found in the inner reaches of the solar system. Its oblong shape is due to the fact that it looks to be two small bodies caught mid-merger. Long ago, two icy bodies found each other in the abyss and collided, but at extremely slow speeds. Just enough for the ices between them to melt and then immediately refreeze, creating a glue that would bind them together for billions of years. Today, the planet Neptune dominates the gravitational environment of the trans-Neptunian objects. Most of these objects live quiet, isolated lives, never encountering another of their kind for millions of years on end. But ever so occasionally, Neptune's gravity pulls in just the wrong way, destabilizing a trans-Neptunian object and turning it into a comet. A ball of ice and rock that loops around the Sun, never lasting many orbits because of the intense heat of our star, evaporating material with every passage. And so out here, in the dark and the cold, these scattered worlds remain. But that is not quite the end of the solar system. The air is cold and crisp on a fresh spring night on the shores of Nordveg in the Netherlands. A young boy is sitting with his father, staring up at the clear sky, watching with amazement as a star streaks across the black. The year was 1910. The streaking star was Halley's Comet, and the young boy would go on to be the famous Dutch astronomer, Jan Oort. One of the few lucky people to spy the comet twice, once in 1910 and a second time, 76 years later, in 1986, from the window of a plane. Oort would go on to be a hugely successful astronomer, but it was comets that would be his lasting legacy, comets that took much longer than 76 years to wait for their return. It was in 1950 that Oort revived a suggestion from decades before and created a coherent, plausible theory to explain the origins of long-period comets. Unlike comets sourced from the Kuiper Belt and scattered disk, these long-period comets seem to take thousands of years or more to make a single circuit around the Sun. They also came from all directions in the sky, meaning that they clearly did not originate from a belt-like structure in the outer solar system. Since these comets could not survive for long when they came within the intense glare of the inner solar system, Oort reasoned that they couldn't have been on these orbits since its inception. There must be a reservoir, he thought, a cloud encircling the solar system in all directions that provided a steady supply of inbound comets. And so after its discoverer, this mysterious source was named the Oort cloud. Objects beyond the heliopause, sitting in interstellar space, but still weakly chained to the gravity of the Sun. However, to date, no object has actually been confirmed definitively to exist within the Oort cloud, save for the comets that occasionally make their way into the inner system. Its members are simply too far away and too small to be resolved even with our most advanced telescopes. But based on the sizes and frequencies of long-period comets, the Oort cloud likely contains roughly 5 Earth masses worth of material. As to its extent, its inner boundary is somewhere around 2,000 astronomical units from the Sun. That's 20 times further away than the heliopause. Estimates suggest that the lonely Voyager will finally encounter it in roughly 300 years. Its outer boundary, however, is unknown, with estimates ranging up to 200,000 astronomical units, or over 3 light-years, most of the distance to our nearest neighbour star. Beyond our solar system is a neighbourhood of stars, many of which formed from the same cloud of gas and dust that gave rise to our own Sun. Within a radius of 20 light-years, there are 131 known objects, including stars, white dwarfs, brown dwarfs, and sub-brown dwarfs, which straddle the boundary between the largest planets and the smallest stars. And while Proxima Centauri is currently the nearest star to the solar system, this won't always be the case, as all the stars in our vicinity, along with the Sun, are in constant motion. In addition to orbiting around the galactic center, they also move in random directions. Indeed, in roughly 1.25 million years from now, the dwarf star Gliese 710 will pass within 0.17 light-years of the solar system. Surrounding our neighbourhood of stars is a region known as the local bubble. It is, like the heliosphere, a region defined by the plasma environment of the interstellar medium. It extends for roughly 1,000 light-years on a side, and its density of plasma is roughly 1/6 of the material surrounding the solar system. Our solar system has been travelling through the local bubble for the past 5 to 10 million years. While its origins remain uncertain, most astronomers believe that a complex of clustered supernovae, detonating one after the other in quick succession, pushed out this void of plasma. Indeed, remnants of these supernovae in the form of rare isotopes of iron, manganese, plutonium and aluminium have been found embedded in the seafloor and in the Antarctic ice sheet. And so, Betoota passed the millennia-long journey in silence. It monitored the changes in density and temperature as it began its first navigations through the heliosheath and out into the interstellar medium through the local bubble. It felt the sting of cosmic rays and diligently repaired the damage. It considered its long-distant ancestor Voyager 1 and its later siblings, bravely venturing out into the endless black. Behind it, the sun grew small and dim, till eventually, as far as its instruments were concerned, it became just another star. After 10,000 long years, Batuta was now plunged into the void, the great depths between the stars. Its interstellar journey had truly begun.
And we're live from the living room as Doug eyes up the match day spread. He's reaching for the buffalo wing.
A 100,000 years had passed since Batuta had first.
I'm Tommy G. Today I'm with United States Marines. If you were to think of 3 words to describe a U.S. Marine, what would you say?
Tough, determined, motivated.
I must shoot him before he shoots me! Say I'm out! Bro, you about to piss me off, scream.
Good morning, ladies! Good morning, gentlemen! Good morning, ladies! Good morning, gentlemen!
This is Marine Corps Boot Camp, which some consider the most challenging military basic training in the world. From the moment a recruit steps off the bus, they are considered federal property, and they are subject to 13 grueling weeks where every moment of their day is tightly controlled. Drill instructors have the job of taking average American teenagers, psychologically breaking them down, and then forging them into a war-ready Marine. Today we have unfiltered access to see what it takes to make a United States Marine. Let's get to it, but first a quick word from the sponsor of today's video. Folks, let me ask you this. If you're doing interviews on public streets, people are coming up, cars are passing by, would it not be a good idea to be aware of your surroundings? Because we know things can change at any time. So there's a reason that you stay aware when things are in motion, just as there's a reason.
Ya. La chicharroni.
Imagine being able to build anything just by thinking about it. Meet Base 44, a complete AI creation platform made for anyone with an idea and a drive to bring it to life. Describe what you want and watch it take shape. You
Chat, I got the Zannies. I got the Zannies in. I got Zannies in chat, yeah. These folks cannot sleep out, bro. found this CPU fully built. I don't know if it's gas chat. I think it's abs. Chica. Why'd you jump out? Okay, good idea. Damn, bruh. Fuck. Rap. Papa sleeps. To that long bar.
Oklahoma is ranked dead last in insufficient sleep. Not good. But the Mattress King has a plan.
I do.
He's going to make Oklahoma sleep again.
What's going on?
The answer is investing in sleep with an adjustable bed from the Mattress King.
For too long, Oklahomans have fallen short of their sleep potential. As your governor, that will change.
Governor? What does that make me?
Johnny, look at the carrot and smile. I'm the Mattress King, and I approve this message.
South Padre is the island for summer days that don't stop at sunset. Plan your summer on South Padre Island.
touch my shit, boy. Get the fuck out of my room. Pepper, you should actually learn to do something.
I am superhero.
Is sex getting tedious? Most men return to
Gotta leave the grape. All of it. Ah. Different. Ah, shit.
This little nigga. Little nigga. Happy beta. They said I hate you.
You're funny, bro. You like to eat all the chocolate? You're funny. You're funny. You're goofy. You're funny. You're goofy. You're funny. You look like a bunny. Yeah, oh, I told you. Give my money, huh? Give my money, bitch.
Christian, what time are you going to your dad's? Because I'm leaving tomorrow morning. So are you leaving tonight or are you leaving tomorrow morning? Huh? What? Do you want me to take you to your dad's or is he going to come pick you up? Yes. You got to figure it out tonight. Tomorrow I got shit to do. I got to go run around the place before I leave. I got to make sure my shit's together before I go. I'm not going to be running around tomorrow. Taking you home. So you need to figure it out tonight.
Alright, Chad, I'm buying some strobe records, just dark web style though. I don't plan on staying out here too long. Sleep my PC, do some resets, reboots, factory resets. Back and go to reset now. Yeah. Another job.